The next two video clips that we're going to look at are pertaining to the last objective, and that is to use the remainder and factor theorems. The first set here that we're going to look at is the remainder theorem. The remainder theorem, it's kind of mathy here, but it's very simple to use. I want to go through what they're talking about here. It says when d at x is the divisor, x minus c. So they're saying d at x is representing the divisor. So they use d for divisor. And make sure that your divisor is a linear with degree 1. So the emphasis is when we divide by a linear factor, the remainder is a real number r. So our remainder has always been some constant, and they're saying it's a real number r. So that the division algorithm simplifies to, and they're coming back to this old strategy that if you take the number you are dividing by, times your quotient, and add the remainder, you'll come back to your original. Okay, again, that was like the 65 divided by 4. We said it went in there once, and then it goes in there 6 times, and then it had a remainder of 1. So what they're saying is if you take the number you're dividing by, your divisor, multiply it by your quotient, which is in this case 16, so 4 times 16, and then add on your remainder, you should get right back to the dividend that you had at the beginning. It's the same thing in real numbers as you have in these functions. Take your divisor, multiply it times your quotient, add your remainder, you should always get your original function you were dividing into, or the original function that you work with. So here's the interesting part of this. If you evaluate f at x for x equals c, now remember that was the part of that divisor, so if x equals c, that is the related 0 that we have. We find that, so we're plugging c in for x, and we're plugging c in for x. F evaluated at c, at this related 0, is c minus c, substituting in, so c, and then q at c. So c minus c, which is 0, times q at c, which really doesn't matter what it is, because we're still going to multiply it times 0, plus r. Really, all we're left with, since this is going to end up with 0, is r, or remainder. So in the bottom line is they're saying if you evaluate your function at c, it will always give you the remainder that you will get after you're done with your synthetic division. So they summarize this key concept as a remainder theorem. And the remainder theorem says if a polynomial f at x is divided by a linear factor x minus c, the remainder that you would get is the same as if you evaluated the function at the related 0 to x minus c. The remainder theorem indicates that to evaluate a polynomial function f at x for x equals c, you can also divide f at x by the related factor x minus c using synthetic division. The remainder will be f at c. Using synthetic division to evaluate a function is called synthetic substitution. Now what we're going to do is we're going to use this process called synthetic substitution to evaluate a function at a given value. So because that's basically what we're doing. The remainder is going to be the same value as if we plugged that value into the function to begin with. So here's the example that we're going to look at using the remainder theorem. The number of tickets sold during the Northside High School football season can be modeled by the function t at x equals x cubed minus 12x squared plus 48x plus 74, where x is the number of games played. So I want to keep track of what that is. Use the remainder theorem to find the number of tickets sold during the 12th game of the Northside High School football season. So we know that what x is, the number of games played, that is the 12th game, so x equals 12. Use the remainder theorem to determine the number of tickets sold during the 13th game of the season. Okay, so now when we come down here, they want us to jump into finding the number of tickets sold during the 13th game. So really, they want us to evaluate t at 13. Well, to evaluate t at 13, we can get a value, but they want us to use this remainder theorem idea in order to do that. So what we want to do is we want to take and do our synthetic division on our function rule, which is x cubed minus 12x squared plus 48x plus 74, we got the x, plus 48x plus 74, and we want to divide this thing by 13. So divided by 13, then we're going to use our synthetic division. So we're going to put a 1 negative 12, 48, and a 74. 3, 2, 1, 0. They're in standard form. We're going to divide it by 13. Okay, we're going to draw our line so that we have a line to put things up and down over the top. So first thing we do is we drop down our 1. 13 times 1 is 13. Then we always add, so that's a 1. 13 times 1 is 13. 13 and 48 is 11, carry the 1. 61. 13 times 61 is a little too big for my head. 13 times 61. So 13 times 61, enter, 793. So I'm going to enter that in this line. 793, I want to add that to 794. That's going to be 7, 16 carry the 1, 867. Now what the remainder theorem says is, if we divide a function by its related 0, then the remainder should be the same thing as our function t at 13, which means we plug 13 back up into the original equation. So everywhere you see an x, you replace it with 13, and we should be able to get the exact same value. So what we're going to do is just quickly find that value. So I'm going to clear that screen off, and now we're going to go 13 squared, or 13, raised to the third power. We're going to add or subtract from that 12 times 13 squared. And then we're going to add to that 48 times 13. And then add 74. And if all goes right, we should get this same number that we have using our synthetic substitution. Or synthetic substitution, which is 867. Those two numbers match. So let me try to square this away for you. Evaluating the function at t equals 13 should give you the exact same thing as synthetic division does, and what you're going to get is your remainder. Okay, so it's an application of the remainder theorem. I don't know if it's as fluid as you would say just plugging in 13 would be, but this is how they're asking you to apply that. So, done with it.